In this lesson, we will describe how the elements of the periodic table were created in the universe. There are many theories of how the universe was created. One theory, which was developed by Einstein, Hoyle, and others, is called the steady-state theory. The current and most popular theory of the creation of our universe is called the Big Bang theory. The Big Bang theory states that the universe formed about 14 billion years ago and has been expanding ever since. All theories state that matter was formed at a very early stage in the history of our universe. The first elements to form in our universe were the gases hydrogen and deuterium. Hydrogen has one proton, P, and one electron, E. Deuterium is an isotope of hydrogen. It has one proton, one electron, and one neutron, N. Deuterium is formed when hydrogen atoms disintegrate into protons, which break down into a neutron and a positron. A positron is a positively charged electron. The diagram shows how the neutron is formed. Protons, neutrons, and electrons are the basic parts of atoms that are used to create all the other elements that make up the periodic table. When protons fuse with neutrons, and electrons are added, deuterium is formed as shown in the diagram. Gases combine to form the stars in the universe. Gravity caused the gases to condense into clumps of atoms at very high pressures to form the first stars. These stars were hundreds of times larger than our Sun. Deep within the center of these gigantic stars, the temperature reached hundreds of thousands, or even millions of degrees Celsius. These high temperatures and pressures caused the hydrogen and deuterium to form helium in a process called nuclear fusion. Unfortunately, nuclear fusion is sometimes called burning, which is not correct, because the process has nothing to do with combustion. The first step in the nuclear fusion process is shown in this diagram. Two deuterium atoms, which have the atomic mass of 2, fuse together to form helium. Helium has the atomic mass of 4. Under the extreme conditions of very high temperature and pressure in stars, the fusion continues. In a process called the proton-proton chain, gamma rays, electrons, and photons as well as subatomic particles called neutrinos and positrons are produced. These nuclear processes are shown in this diagram. The extremely high temperatures and pressures generated by the nuclear fusion process causes helium nuclei, also known as alpha particles, to be converted into elements with larger and larger masses. This results in the so-called triple alpha process, which enables helium to be converted into beryllium and carbon during nuclear fusion. This diagram shows the triple alpha process. In this process, 2 atoms of helium fuse to form beryllium. Then, 1 atom of helium fuses with 1 atom of beryllium to form the element carbon. Carbon is the first key element of life. Once the most stable isotope of carbon, carbon-12 is formed, the other life-supporting elements, oxygen and nitrogen, are formed in the sequence shown in this diagram. This is called the CNO cycle. Starting on the right, the diagram shows a proton added to carbon-12 to form an isotope of nitrogen. The other isotopes of carbon and oxygen are then formed by the addition of protons and the loss of neutrons, positrons, and electrons in the CNO cycle. Now, let us look at the various stages of how the stars evolve. In the first stage, when the star is formed, only helium, He, is formed at the core. In stage 2, after the hydrogen is used up in the core, the helium begins fusing into carbon, C, at its core, but hydrogen continues to form helium in a thin layer farther out from the center of the star. In stage 3, the star swells to become what is called a red giant. During this stage, the smaller elements fuse together to form larger and larger elements. This diagram shows cross-sectional views of the first three stages of a star's formation. In stage 1, at the top left, hydrogen is fusing to helium in the core. In the outer part of the star, no fusion is taking place. As the star grows into stage 2, shown on the right, hydrogen begins fusing to carbon in the core, while hydrogen continues to fuse to helium in the zone just outside the core. In stage 3, on the bottom left, the star forms into a red giant. At this stage, carbon fuses to sodium, neon, and magnesium in the core, while helium fuses to carbon and hydrogen fuses to helium in the zones outside the core. Stage 4 is the final stage. In this stage, elements such as sodium, neon, magnesium, oxygen, sulfur, and silicon are formed in the outer layers. Also in this final stage, the heavier elements are formed closer to the core, and eventually fuse in the core of the star to form iron, the most massive element found in stars. In this diagram of stage 4, the heaviest elements are formed close to the core, while the other elements are formed by fusion in the outer layers from the heaviest close to the core, to the lightest in the outer layers of the star. After a star reaches stage 4 in several billion years, it undergoes a massive explosion. This explosion is called a supernova, and it completely destroys the star. The extreme temperatures that occur during this supernova explosion are estimated to be more than 100 million degrees Celsius. This enables atoms, neutrons, and other subatomic particles to be released at an enormous rate. This astrophotograph shows the remains of a supernova explosion called a nebula. Because of its shape, it is called the Crab Nebula, and it occupies a space that is over 5 light-years in diameter. This nebula is estimated to be 6,523 light-years from Earth. That distance is 38,346 quadrillion miles. In scientific notation, that is 3.8 times 10 to the 16th power. All the elements heavier than iron are formed in a supernova explosion, where neutrons and other subatomic particles are released. When an atom captures a neutron, it becomes a heavier isotope of the same atom. Many of these isotopes are unstable, so the captured neutron decays into a proton, electron, and neutrino, as shown in the diagram. This converts the atom into the next element in the periodic table. The process continues until all the heavier elements are produced. This diagram shows how elements heavier than iron are formed in a supernova explosion, when neutrons are captured by lighter elements. When a neutron is captured by a light element, the new heavier nucleus becomes unstable, so it releases an electron and a neutrino in what is called beta decay. This leaves an added proton in the nucleus, resulting in the formation of a new element. Now let us look at how the elements reached the Earth. When stars and supernova explode, they send burning pieces of matter in all directions. These hot pieces of matter, which contain the various elements, spread throughout the universe to eventually form other stars and planets. In this way, our solar system was created over a period of many billions of years. This astrophotograph shows what is called a planetary nebula, the remains of an exploding star. It consists of an expanding glowing shell of ionized gas ejected from a red giant star late in its life. This nebula has the name NGC 5315. NGC stands for the New General Catalogue, which is a catalogue of 7,840 deep sky objects. This nebula is 7,000 light-years or 4.1 times 10 to the 16th miles from Earth. This bibliography provides references to articles with more information for students who want to further study the origin of the elements. This presentation was produced as a public service to help middle school and high school science teachers develop experiments, presentations, and demonstrations that can be used in their classes. More science experiments and demonstrations are available on the Tops of Santa Clara Valley website, www.topsofscv.org. TOPS, Teaching Opportunities for Partners in Science, is a program aimed at stimulating greater interest in science by middle school students.